Thank you. Thanks everyone, and thanks to the organizer for giving me the opportunity to talk about my research. I'm going to speak about this project with Nick Connolly, Vivien Londe, and Anthony Leverrier. So I'm going to talk about quantum LDPC codes. You must be convinced now that we need quantum LDPC codes, and we need a decoder for those codes. And I'm going to spend some time telling you why we should work on the erasure channel. So first, we have those good quantum LDPC codes that we heard about this morning. And we have decoders for these codes. They have linear complexity, and they can correct a linear number of errors. Both of these things are optimal. But in practice, the quantum LDPC code that we see bit surface code with realistic noise model, with circuit level simulation, are not the same. We have 3 simulations here that show that we can bit surface code. We can use fewer qubits for a fault-tolerant quantum memory. And they use different codes that are not necessarily those optimal asymptotic codes. And for these codes, we would like a decoder. We would like a general decoder capable of decoding any sparse quantum code, any quantum LDPC codes. So 2 of them, for instance, are the BPOSD decoder that works very well in practice. It's a heuristic, but it works very well. Or the union find decoder that we can adapt to LDPC codes. This adaptation doesn't seem to work as well as BPOSD. There is more recent result I will mention later. And the goal is to reduce the complexity and improve the performance of this kind of general decoder. And why the erasure channel? So first, the erasure channel it's a very old noise model. In the classical setting, it was introduced by Elias in the 1950s, and it was introduced as a toy example. Why? Because it's simpler than the bit flip channel, the binary symmetric channel, and it's always easier to work with a simpler problem, to start with a simpler problem. And in the quantum setting, it's going to be a simplified depolarizing channel. So it's a simplified version of our noise model. And because it's a simplified version of this common noise model, we can transfer ideas. It's very powerful, and it's exactly what happened in the classical setting. We transferred ideas to achieve capacity, to build optimal codes for classical error correction. And we managed to transfer ideas to reach optimal codes for the binary symmetric channel, for the bit flip channel. So let's do the same thing in the quantum setting. And another place where we see that is with the union find decoder that we designed by first designing an erasure decoder, and it's a subroutine of the union find decoder. And because it's a subroutine, if we speed up this subroutine, we speed up the whole decoder. So it's also something we're going to use here for LDPC codes. And it was introduced as a toy model, but it's actually a practical channel, both classically with the TCP communication, or with the quantum setting, with this erasure conversion that is very popular. If you can detect errors, it's easier. And this is exactly the erasure channel. And to show you that it's a technique that works, I went through the recent winners of the Shannon Award. It's the most prestigious award in information theory. So Urbanker is one of them, and he won for his work on the erasure channel, binary erasure channel. They proved with collaborators that you can achieve capacity with LDPC code. You can build optimal LDPC code. It was proven in 2014. It's not one of these results. But the first step was to design optimal codes for the erasure channel, and all the techniques that were used to design those optimal codes transfer because the channels are similar enough. It's a very powerful toy model. And it took 50 years to prove that they achieve capacity, LDPC codes. So it's non-trivial result. And another one is another family of capacity achieving codes. It's polar codes. Here there is no erasure channel in the title, but if you open the paper, you are going to see binary erasure channel 61 times, because the whole idea was developed over the erasure channel. And if you explain it over the erasure channel, it's very clear. It's not trivial to move to the binary symmetric channel, but once you have the idea, it works. And another one, also Shannon Award, he worked on the capacity of the quantum erasure channel. Why? Because it's still an open question today. What is the capacity of the depolarizing channel? We don't know. We don't even have a conjecture. But if you move to the erasure channel, we can exactly compute the capacity. So this toy model is very powerful. And that's why a big fraction of my paper have erasure channel in the title. It's simpler. So now I'm going to briefly review those classical and quantum erasure channel, and we're going to design decoders for this model. So if you have no noise, you will send a bit onto itself. You will keep a bit unchanged with some probability 1 minus p. And if you have noise, you send it onto a question mark. You receive a question mark, you know that the bit was lost. That's the classical erasure channel. So if you send a bit string, you receive something like that with some question marks. And when I tell you it's a simplified bit flip channel, it's because I can pick those question mark and replace them by a random bit. And then I obtain some bit flip channels applied only to the red bits. So it's a bit flip channel where you know the positions that are potentially flipped. So it's really a bit flip channel with some extra information, the location of the bit flips, of the potential bit flips. And in the quantum setting, we can do the same thing. We can map a state onto itself with priority 1 minus p. It's preserved, no noise, and map it onto some erased state. What this means is that it's a state that is orthogonal to the computational space, the space that contains this density matrix. So you can measure if you left the computational state. And when you send a state through the channel, you obtain something like that, where some state may be replaced by this orthogonal state. And we can do the same thing. We can say, this orthogonal state, let's replace it by a maximally mixed state. And so if I do that, I get something like that. And this maximally mixed state, we know that it satisfies this identity. So it's equal to a quarter of our state with no noise, our state with X noise, Y noise, or Z noise. So it's basically a random bit flip. It's a Pauli error, identity X, Y, or Z, each with a probability a quarter. It's basically the same noise as classically. So we have the same thing. Our quantum erasure channel, it's basically a simplified depolarizing channel, simplified Pauli noise, where you know the locations of errors. Okay. So now we can start. We can try to decode that. So in the classical case, we're going to use LDPC codes. So LDPC means low degree. And we define a code by a graph, the Tanner graph that we saw this morning. You place bits on the circle, on the bit nodes, and you place constraints, linear equations, on the circles. So everything is going to be mod 2. And this check is guaranteeing that the sum of the 3 incident bits must be 0 mod 2. For example, the Hamming code, in the quantum setting, it's the Steen code. If you flip a bit, you are going to detect that the 2 incident checks here are violated. The parity is not 0 anymore because you flipped this bit. So those 2 checks are violated, and the other check remains valid. Okay, now how do we use this information to decode? So we have a bit string with some erased bits, and we're going to try to recover those erased bits. I'm going to call that the Gaussian decoder because it's basically running Gaussian elimination. We will start by replacing those question marks by 0. We keep in mind where are the question marks, but let's assume it's a 0. And now we can compute the check values. So if I compute the check values, I get 3 parities, and I'm going to look for a bit string inside those 3 erased bits that give me the same check values. Why? Because if I get that, I will find a bit string that give me the same check values. By adding this bit string to the question mark, I get valid checks. So I'm back to the code space. And this is how we correct. And this step 3 is actually Gaussian elimination. We solve a linear system. It's a bunch of linear equations. So we can do it in cubic complexity. Or better, but worst case in qubit complexity. And what we would like to do is to do that, but in linear time. And we are going to use something called the peeling decoder, which is rooted in old Russian literature. And the idea is to use a dangling check. A dangling check, it's one of these squares, but which is incident to a single erased bit. So for instance, if I look at this first question mark, this first check, it's incident to my 2 question marks. It's not dangling. But the second check, it's incident to 1, 3, 5, 7. So it's incident to a single question mark. It's a dangling check. So let's use it. And the algorithm is looking for dangling checks. Then you use it to correct the incident bit. And how does it work? I find a dangling check. There is one equation associated with this check. Sum of the incident bits is 0. And I replace the bits by their value, except the missing one, the question mark. And that gives me an equation that reveals the question mark. So I can correct with that, and there is a way to implement this algorithm in linear time. It's called the peeling decoder. And it works in some cases, if the erasure is simple enough. So here, if we run it, we find x2, and then we look for another dangling check. We can take any of them at this point. So this dangling check gives us an equation that reveals x3. Okay, now this algorithm works in many cases, but not all the time. So when does it break down? It breaks down if we see a stopping set. And a stopping set, it's a set of erased bits with no dangling check. It's kind of obvious by definition that the algorithm is going to fail. There is no dangling check, so we cannot peel anything. We cannot use them. And this is an example. The first check is incident to the first 2 question mark, but not the third one. The second check is incident to number 2 and this one. And we can check that the third check is also incident to 2 of them. And what they prove, Ziabloff and Pinsker, is that the peeling decoder fails only if and only if we encounter such a configuration. The set of question mark contains a stopping set. And then, knowing that, we can design codes that have very low probability to contain a stopping set. It's what Richardson and Urbanker did. With the erasure channel, they designed codes such that by selecting the graph in a careful way, you can assume, you can show that there is no stopping set with high probability. So the algorithm never fails, and you can decode with probability that goes to 1. And the basic idea is to design a graph with no short cycle, with large curves. Okay, now let's do that in the quantum setting. So first, the quantum Hamming codes. So I told you this is a Hamming code. If we have a flip, we detect the bit flip on the incident checks. It flips one of the checks. It flips the incident checks. And we do that by computing parities. In the quantum setting, we saw Dom's examples. We correct X and Z errors with 2 types of checks. So if there is an X error, it's detected in the bottom by the Z checks. And if there is, and those are measuring a parity operator. So it's basically computing a parity in the quantum setting. We measure either Z or we measure X to detect Z errors. And it gives us a sand drop. So it's a very similar picture, but there is 2 types of checks. And now, let's adapt the naive decoder, this Gaussian decoder with cubic complexity. We have some question marks, and those are the 3 steps of the classical Gaussian decoder. Let's adapt them. So first, we are going to replace our question mark by identity x, y, or z. It's what we can do by using our identity about the maximally mixed state. Then we are going to measure the check values. And we are going to look for a Pauli error included in the question marks that has the same checks, that give me the same checks. That will allow me to cancel the error. And we can do step 3 again by Gaussian elimination, which costs again n-cube operation. And we can prove that it's a ML decoder. Proving that is a bit more complicated than in the classical setting. I will not say complicated, but there is some subtlety because of the equivalence between errors. Errors are equivalent up to a check, up to a stabilizer, but we still have this property. Okay, now I'm going to look at surface codes. We have a cubic complexity decoder for erasures. We want to reduce the complexity. And surface code, it's the first case where we notice we can do it in linear time. So the Tanner graph of surface code, this graph with x and z checks look like that. This is a 5x5 surface code, and you have alternated x and z checks. And we're going to focus on the correction of x errors. So we look only at one of the 2 subgraphs, so one corresponding to one type of checks. It looks like a square grid, and an erasure looks like that. So we have a set of qubits. The qubits are the circle. Some of them are erased, and I'm going to color in red erased qubits. So you have a red edge for erased qubits. So here there is this cluster of erased qubits, and we want to apply this algorithm. So the algorithm is going to start by the same thing, while there is a dangling check. So a dangling check is this one, for instance. It's incident to a single question mark. You pick a dangling check, and you use it to correct the incident qubit. So here we're going to use this check to correct this qubit. And how does it work? We know that this check has value 1. It's telling us that there is an odd number of incident, an odd number of x errors on the incident qubits, but it can only be inside this erasure. So it must be a x. We must have an x here. And we can do the same thing with the next check. Now that we corrected this qubit, this one becomes dangling. So we keep doing the same thing. We can correct again, and we apply an x error because this check has value 0. The number of incident x must be even. And we can do the same thing with the last dangling check up there. And in this case, we get the identity. Now there is no more dangling check. So the classical algorithm fails at this point. It's a stopping set. Every check is incident to at least two erased qubits. Nothing dangling, we cannot peel anymore. And what we're going to do is that we're going to add a step. We remove an arbitrary qubit. We remove an arbitrary question mark. It seems very violent, but the structure of the surface code allows us to do that. Why? Because, so I'm going to select an arbitrary question mark and remove it. And I'm going to tell you here, there is no error. So I'm telling you there is no x error. And why I can do that? Because when there is, because this edge is part of a cycle, which is a stabilizer of the surface code. It's an error that fixes encoded code state. So if I have an x error here, I can just multiply by this trivial error that does nothing to my quantum state, and it's going to remove my x for free. So I can assume that there is no x on one of the qubits, only one. And when I have done that, I can keep peeling. So I'm going to remove everything I can, until, again, I'm stuck, and I reapply 4. So I select a random erasure, and I remove it, because this set of 4 qubits is a stabilizer of the code. It's an error that has no effect. So I can assume there is no error here. And by doing that, I'm going to I'm never going to be stuck. I'm going to find a correction inside the erasure. And we can prove that it's an ML decoder, and it can be implemented in linear time. And a better implementation, I will say, is to use a spanning tree of the set of erased qubits. I will barely comment on that at the end. Okay.
Nicholas, I have a question. Do you assume that everything works exactly with 0 and 1s, or almost, or I mean, if you do these checks, or?
I'm assuming that my check value is 0 or 1, yes. Yeah. It cannot be a soft information. If it's soft, I don't know exactly how to adjust that, but I think we can. If it's soft, it's probably not an erasure model for which we have a linear time decoder easily, okay. But we can make it work with more complex decoder. Yeah, I'm going to be doing only combinatorics. Everything is going to be discrete and nothing continuous. So now we want to adapt that to LDPC codes, and we're going to work with hypergraph product codes, with one family of LDPC codes. So first, I'm going to review that very quickly because you saw them this morning. They are built by taking two classical Tanner graph, so two classical codes, one horizontal and one vertical. And what you do is that you take the Cartesian product of those graphs. When you take their Cartesian product, you have 4 types of nodes: circle times circle, circle times square, square times circle, square times square. Okay. So the first type is circle, circle. And for those, you place a qubit on them. So there is 9 qubits here. For the second type of qubits, it's square, square. Here you have 2 qubits added. So you have a total of 11 qubits. And now you need to fix the checks. You're going to define 2 types of checks, one on circle square, and the other one on square circle. So for those checks, you are going to define a X check starting from each of these 6 vertices. 6 vertices. And you do it by having vertical edges that correspond to the vertical graph. So this one comes from this vertex, which is incident to the first one and the second one going up. So we do the same thing. We add an X on the first one and second one going up. And horizontally, we add the horizontal edges of this horizontal graph. So we get one X here. We do the same thing for Z checks. And for Z checks, we obtain something like that, where horizontally, we use the horizontal edges. So there is 3 of them in this case. And vertically, we use the vertical edges of the corresponding vertex. And you can notice that they commute. They overlap on an even number of positions. We do that for the 3 Z checks and the 6 X checks, and we obtain a family of LDPC code with good enough parameters in many cases. And they can beat surface codes. And the key observation of our most recent paper is that if we look at a horizontal X error that is included in a single row, something like that, if it has support in a single row, then the syndrome of this error, when we evaluate the checks, it corresponds to the classical code syndrome. Why? Because the only checks that are connected to this row come from those 3 vertices. If it's an X error. There is checks coming from those, but those checks are X checks that will not detect the X error. So it's a trivial observation, but we are going to reduce the decoding problem of the quantum code to the decoding problem of those 2 classical codes, thanks to this observation. So I will need to tell you how do we reduce the problem to a single row. In general, errors will be everywhere. And we have the same observation vertically for a vertical X error in square square. So there is qubits here. It's a vertical error here. Then the syndrome is also the syndrome of a classical code, but looking vertically inside this code. And because qubits are supported on square square, we'll put bits here. So it's a classical code where we reverse the roles of squares and circles. Okay. Now that we're there, let's start designing new decoders. And the story of this paper is that we're going to iterate a design process, which starts by a naive decoder, and then we're going to find the most common stopping sets, the most failing configuration. So if you look at the paper or in this presentation, I'm going to have a lemma that say the decoder fail if we have that. And the lemma is complicated sometimes, so I'm not going to even read it all, but I'm going to highlight some parts. And once we understand why the decoder fail, and this is the dominant source of failure, we can design a new decoder. We can modify the decoder to design a new decoder where we can correct the most common failing configuration. We're going to do that 3 times. And after 3 times, we're going to check numerically that the performance is pretty much optimal. And I won't prove it. We don't know how to prove it. But numerically, we see that it's almost optimal. OK, so first version, we have a lot of experience with classical error correction, so let's use that. Let's use the classical peeling to decode quantum LDPC codes. We have 2 types of checks, but we can apply twice the classical peeling. So we're going to use general CSS codes, and we're going to apply the correction of, we're going to run the classical decoder to apply to the correction of X errors. Using the Z checks, we can run the classical peeling. In some cases, it's stuck, but if we are lucky, it's going to work well. And it's going to correct X errors. We do the same thing for Z errors, swapping X and Z. We can do that for any CSS code, any code defined by 2 types of checks. And does it work? Our issue was that if we run the simulation, it corrects only a constant number of errors. It's supposed to correct square root of n errors. It corrects only a constant number of question marks. And our first lemma, the failing configuration, is that if the support of X stabilizers is covered, we cannot correct because it's a stopping set. So the stabilizers are defined, the checks have low weight by construction. LDPC code have low weight checks, and they are stopping sets. So by construction, quantum LDPC code will fail for this decoder. They are the worst we can imagine. So let's modify it. We know that we need to get rid of those erasures that cover a stabilizer. So let's just do that. Let's add a step that does that. And we're going to call it pruned peeling decoder. And it's basically similar to the case of surface code, where we have those stopping sets that correspond to stabilizers, and we were removing an edge arbitrarily. So let's do the same thing. We can start with the same decoder. We select a dangling check and we use it. And when we have no more dangling check, we select an array stabilizer, but we had a condition here. We don't select an arbitrary array stabilizer because there is many of them. We select one that is a product of up to m stabilizer generators. It's a product of m checks. And m is going to be small. And we remove 1 qubit arbitrarily. Because we do that, we know that by multiplying by this stabilizer, we can remove the X error on this qubit. So we are allowed to assume that there is no X error on this qubit. But finding this stabilizer is not always trivial. This can be done in linear time for surface code. It's what we saw with surface codes. In general, we didn't figure out how to do it for general LDPC code because there is an exponential number of stabilizers. If any of them can be covered, we don't know how to find them. But what we can do is that we can look for a single stabilizer generator. If there is a single check that is erased, we can check that. There is a linear number of checks. We can just go over all the checks. And we went up to m equal 2. So we look at a single check or a product of 2 checks that are erased. And by doing that, you will see at the end on the numerics that doing that is enough. It allows us to achieve a good performance, only assuming m equal 2. And looping over all the product of stabilizer is efficient enough. And in numeric, m equal 1 is actually even enough in many cases. OK, so now I told you we are going to look at the decoder and then look at the most common failing configuration. It's our second step. We are going to do it again. So there is another lemma. Don't read it. but it's just to show you the structure of the process. So we have a lemma that tells us the most common configuration is this thing. It's horizontal and vertical stopping set. And I'm going to tell you, if there is a stopping set in the classical code here, then there is many stopping sets in the quantum code. Why? Because each time I take one bit here, I can build a new stopping set. There is many copies of this stopping set. So basically, you have square root of n copies of one stopping set. So if we were saying we design classical code such that stopping sets are rare, but even if they are rare, there is square root of n copies of each of them. So the quantum code is going to have a new problem that this Cartesian product structure creates many failing configurations. So we need to get rid of them. And that's what we're going to do with the VH decoder. That's our last iteration, and this one is going to achieve a good performance. So it's VH for vertical, horizontal. And the two graphs I'm going to talk about are the vertical subgraph obtained by selecting only vertical edges in our Tanner graph, or only horizontal edges. So it's just square root of n copies of the same graph, of the horizontal graph or the vertical graph. It's the other way around. And now we are going to define clusters. We're going to use those graphs to partition the error into clusters. So let's forget about X checks, because we look at X errors. They are only detected by Z checks. And we are going to define the horizontal graph. So we have the horizontal graph and the vertical graph already defined. So this is the horizontal graph. And we are going to define our set of erased qubits. Here they are in red. There is 3 erased qubits and 2 checks. And we are going to define E bar as adding the checks incident to erased qubits. So we look at erased qubits and incident checks. And this set, it's a subset of vertices in a graph. We are going to define clusters as connected components in this graph. So here I have 2 clusters, one here and one with these 2 vertices. Oops. So this is one cluster. OK, now our set of errors, our set of erased qubit looks like that. It's a bunch of clusters. There is horizontal clusters, and there is vertical clusters, and they are connected through Z checks. And the main observation is that we can define a graph on top of this graph. So we move to a higher level of abstraction where each cluster is going to be a vertex. So here you have one vertex here, another one here, and so on. And we're going to connect this vertex if they share a Z check. So for instance, here, this is a Z check. It's connecting this cluster and this cluster. So there is an edge connecting these two. So those edges, I'm not going to draw them because they are basically going through the check like that. And the observation is that it's a bipartite graph. There is 2 types of vertices. There is horizontal clusters and vertical clusters. There are 2 types of vertices. And they are never connected with each other. There is no connection between 2 vertical clusters. Otherwise, they will belong to the same cluster. They will be the same cluster. So that's what that means, bipartite graph. You have connection between those and those only. And the Z checks are edges. You see that there is each Z check connects one horizontal and one vertical cluster only. So it's really an edge. You can remove this symbol, and it's an edge connecting 2 clusters. So there is really a graph structure on top of these clusters. So now, let's correct in this graph. So the first thing we're going to do is that we're going to look at the most simplest part, the isolated clusters. It's a single cluster. It's not connected to anything else. And all of them have a small size. They are included in a row. So they have at most square root of n vertices. So I'm going to do the most brutal thing I can do. I'm going to just decode this thing with a Gaussian decoder. But because this cluster is small, the complexity, even if it's cubic in square root of n. So it's n to the 1.5 here. It's square root of n cubed. So it's small enough. It's at least small. Now, we have no more isolated clusters. Let's look at the second simplest type of cluster. And it's those that are connected to a single other cluster. So it's dangling cluster. It's exactly like our dangling checks in the surface code, but at a higher level of abstraction. And a dangling cluster, it's a cluster that's connected to a single other cluster. So there is a single Z check, C, that's connected to another cluster. And what are the properties of these clusters is that if we look at the value of this check, there is two cases. We're going to call it frozen, this dangling cluster, if when we look at all possible correction we can apply in this cluster, all possible errors we can find, they have the same value on this check. If they all have the value 1, for instance, then it's a frozen value. We cannot change it. It's fixed. And it's free if there is some correction that has the value 0 and some other corrections that has the value 1. Then we can choose this bit. So keep in mind, frozen means the value of C is fixed. And now, let's adapt our peeling decoder. So what we did with the surface code, select a dangling check, use it, select a dangling check, use it, until we are stuck. We can do it here at the level of clusters. So we're going to look at frozen clusters, and while there is a frozen cluster, we select it, run Gaussian elimination in this small cluster of size at most square root of n, and we update the value of the syndrome here, the value of C, and we remove this part from the erasure. So we can correct a dangling cluster if it's frozen. And if it's not frozen, we need another process. We're going to correct free dangling cluster as follows. If it's free, the value of C can be either 0 or 1 by finding one of the two possible types of correction here. So we can do it, delay the correction until the end. We can decide later if we use a 0 or a 1. We don't want to take a premature decision and say, let's pick a correction that gives us 1, and then this cluster may be unable to find a valid solution with value 1. So we're going to delay it until we can correct that at the very end. So we select the dangling clusters, and if they are free, we remove them. We just remove them and put them in a stack, and we're going to correct that later. So we have a stack of free dangling clusters that we're going to correct at the end. Okay, so I'm almost done. I want just to show you the high-level picture of the algorithm. That's the pseudocode from the paper. We're not going to read it, unless you want to. No, I'm not going to read it. So the first step is correct isolated clusters, and we apply the same process to correct frozen dangling cluster, Gaussian elimination. The second step, I told you, if we see a free cluster, we place it in a stack for later. We can delay the correction. And the third step is correct the remaining free clusters at the end. And if we are lucky enough, by getting rid of those two types of cluster, we can peel this cluster graph until there is nothing remaining, and we can correct the whole thing. Now let's look how it works. So the Gaussian ML decoder is here in the bottom. So the horizontal axis is the noise rate. It's erasure rate. And the vertical axis is the logical error rate. So when there is less noise, it goes down. The logical error rate goes down. The decoder fails less often. And the ML decoder is the one in the bottom. It's the purple one with the best performance. It's optimal decoder, but it's cubic complexity. Then our first decoder was the print peeling decoder with m equals 0. It's in blue. And we picked m equal 1. So when we are stuck because of a stabilizer, we just remove an arbitrary qubit of one stabilizer. We get the yellow plot here. So we gain 1 order of magnitude of performance. And after that, we can say maybe there is product of 2 stabilizers that are erased and that we did not detect. So it's m equal 2. By doing that, we gain nothing in performance. It's almost the same thing. So we are going to stick with m equal 1. Sorry, this should be m equal 1. So in the print peeling decoder plus vertical horizontal VH decoder, which is peeling vertical cluster and horizontal cluster. Then we gain another order of magnitude, and we are at the red plot. When the noise rate is small, it's pretty much identical to the failure rate of the optimal decoder. And there is a small gap for high noise rate, which we care less about. We are mostly interested in low noise rate. So it works well, and it doesn't only work well for this code. We generated a bunch of random codes, and for all the codes we simulated, we observed the same thing. So these are 4 of them, with different code lengths, with 600 qubits, 1200 qubits, 1600 and 2000. And in each case, you observe that there is a smaller or bigger gap, but the red and purple plots are our decoder and the ML decoder, the ML Gaussian decoder. So the gap between our decoder and the optimal decoder remains very small, especially in low noise rate. We cannot prove it, but numerically we observe that it works. So it will be good to prove that asymptotically it works. And I'm going to conclude here. So we have seen, so the decoder that we obtained, I didn't mention the complexity, but it's n to the 1.5. So it's almost linear time in that sense. And it's because the erasure noise model is a simplified version of this depolarizing noise, we can directly plug it in to speed up other decoders. Speed up the BPOSD decoder, which corrects an erasure as a subroutine, the union find decoder, which corrects an erasure, and another recent decoder that appeared just a few weeks ago from Krishnan, Avon, and Wouters, which also reduces the decoding problem to an erasure. So those 3 decoders can be immediately speed up. And another thing, we can go from erasure to depolarizing channel. Just like we saw in the classical setting, the ideas that we designed for the erasure channel that we designed last year are actually working in the bit flip channel. And this is another recent work from some of the same people, Stembler, Krishna, and Beverlen. And what they do is that they use a small set flip decoder that we can see as a bit flip version, a depolarizing version of the peeling decoder. It's a local decoder, but it gets stuck in some configuration. And it gets stuck when the residual error is inside a row or inside a column. It's exactly the same patterns. So we can do the same thing, use a decoder that works inside a row or inside a column. And I find the similarity interesting. I think it's the classical story is instructive. It repeats its useful intuition. And I want to conclude with some open questions. So first, we're at n to the 1.5. I was aiming for n. And I find it very curious. I will bet that there is a linear time decoder. We were just not smart enough to find it. I think it's a very interesting combinatorial question, but also because n is very big in practice for LDPC codes, it's actually a gap that can be significant. We need fast decoders, and you have to think of large n. So it's also practical. And our final decoder is using the structure of hypergraph product code, this product structure. We would like to generalize it to have an erasure decoder for a general LDPC code with no specific structure beyond the sparse graph. And another open question, because I talk about LDPC code, I have to mention it, is find the right hardware. So Ari told us about one way to have a hardware that's flexible for LDPC codes. Yeah, we need more work to know how to make them work with other platforms and even to make them work with large number of qubits, with large codes. We simulated codes with length thousands, and it's the regime of LDPC codes. It's thousands. So we need more hardware improvement. And another related question I want to mention that I find very curious, it's the case of color codes. I told you that we can have an ML decoder that is optimal for erasure and that works in linear time for surface codes. Color codes are very similar. but they are different enough so that it seems harder. At least I don't know how to do that. To have a kind of peeling decoder that works, that is optimal in terms of performance and complexity for color codes. I'm wondering if it's possible or if it's n square. And the underlying question is related to spanning tree in a hypergraph. We use a spanning tree in a graph to make it work for surface code. As soon as we have a hypergraph, it's more complicated. The structure of spanning tree is much more involved. Thank you.